Hello and welcome to Selected Topics from Basic Stats, which is the review of Basic Stats, the course that you took in previous semesters. So today we're going to cover some of those material, the basic descriptive statistics, and then the next few weeks we're going to cover more. And once we're done, then we switch to more heavy-duty advanced statistics material. And like I mentioned before, the statistic is cumulative, so you need to go back and relearn the basic stuff. We started with the population and sample. And this is the analogy I used and said population can be a university, a hospital, can be a city, can be a country. But here I have the population as a large pizza. So imagine there is a huge pizza and then you wanted to know about this pizza, like assuming it's all the same topping. So you don't have to eat the whole thing to find out whether it's too saucy or too doughy or you don't like it or other information. All you have to do is just one slice, assuming that slice contains all the ingredients and information that the entire population has. So same thing, if I want to get some information from Albizu University students, all I have to do is just have a sample of students. Let's say if their population is 1,000, then I use sample of, let's say, 200 or so. There is a formula to come out with the appropriate sample size. We'll talk about that too. And then whatever you find out about that sample, the standard deviation, variance, mean, and all that stuff, that's descriptive. Then you apply that to the population, to entire body of students, let's say at Albizu University. And the statistics, like I mentioned before, you take in this course to help you with research. That's your dissertation, doctoral dissertation. So that's the reason for, so it's good to understand that whatever you're learning to apply that to your dissertation. And again, I try not to say this every time, but unfortunately I always do. One of my goals for you guys is to start thinking about your hypothesis, doctoral dissertation topic. And this way you will learn once we go over these tested statistics, you get an idea which one you should use for your quantitative research. And then again, descriptive too, if it's, qualitative, you can always use those little guys too. So to apply that to what we're doing in the statistics, what you're looking at now is a distribution, which is normal distribution with or bell-shaped distribution or symmetrical distribution. If we assume that distribution is like population, that large pizza, then let's say it's Albizu, Albizu University, with 1,000 students, we can take unlimited samples from this population. Unlike the pizza, that once you took, all the pieces, all the slices are gone, then population is gone. But it's not the same in statistics. In a statistic, you can take unlimited samples and still the population maintain the same. Unless, again, if it's one semester, unless longitudinal, that means every semester the number of students changes, go up or down. But assuming it's just once this semester, okay? So if I take a sample of 200 students, and one of those is square in that bell-shaped distribution will be my sample. So if there's 1,000 students, you might say, well, now there's 1,800. No, still we have a population of 1,000 students because those students will go back to the population. And then the next person can use a sample of 500 or 300 or 100 and beyond. But still the population remained the same. Each one of those squares, now if I make it larger, contain a sample. That red line right there at the bottom, it says mu, okay? That's mean. Mean is a Greek letter. It stands for mean or average. So if I take a sample, then I can calculate its standard deviation, variance, mean, and beyond for the sample. But first thing you're going to learn is that sigma m that I put in is called standard error or standard error of the mean. We need that because, again, in your research, you want that standard error to be low as it can be, just like it sounds. It says error, so you want the error to be low in your research. It means that if you really take hundreds of samples from this population, like find 100 researchers or just yourself doing it, and you calculate the standard deviation and the variance, the mean of all those standard deviation, the mean of all those standard deviations will be a standard error. So that's how you make a comparison. The standard error has its own formula, and this is not how we measure it. We measure it by using that little formula that we're going to go over it shortly. So this is the definition of sample that we just talked about, and there is a formula to come out with the right size of sample. And then it tells you that make sure your sample is representative of population. That means if you decide to work with children, so make sure they're all children. And then again, that right there link should give you the sample size, the correct sample size. The next topic we covered was variability. Again, variability means the changes. But what changes with variation, variable? What are we talking here? We're talking about the variation, the variability under the curve that I just showed you, that bell-shaped curve. Some score are on the right there in the middle, mean. Some are above the mean, some below. So if I have a class and I want to see how they're doing, I wanted to see where their scores are for the midterm. Are they on average? How many people are above average? Or how many people below? So when you have a class of like large class size, you see where the students stands, whether they are in the middle, which should be in the middle, average. That's what the mode is, the most frequently scored. And then again, mean, and then you have the median. We use these statistics, descriptive statistics, to calculate the variability. And we use it because of the changes to see where we stand. For example, if the mean for class is 70 and the standard deviation is 10, then somebody say, well, how did I do? One of your students will say, how did I do? Then let's say if that person score 80, so we say you one standard deviation above average students. This is how we can tell based on the standard deviations and variance. So we need to know that. Also, there are other uses for these standard deviation and variance that we mentioned, we talked about in descriptive statistics last semester. For example, variance, the number you get, it tells us about a quality of our test, just like reliability. The higher the variance, that means if you have a test consists of, let's say, 100 items, which is too many, and you wanted to get rid of 10 of them, if you calculate the variance for each item in your test, you will get rid of the one with lowest variance. That's one use. Because they have a low quality, low variance, low quality items. So that remaining 90 will have a higher, it's a better test. We get rid of 50 of them. It doesn't matter. This is how you do it. You don't just look at it. That's part of the test construction that I used to teach. But I don't think it's there anymore. So, and you should know how to calculate standard deviation, variance, but your first quiz and SPSS is about calculating standard deviation, variance, mean, median, mode, or measures of central tendency. And that's what we're going to cover shortly. And we're going to go over them. It shouldn't be hard at all for you. It's just refreshing your mind. So there's a definition. Again, variability is a measure of dispersion, meaning spreading of score around the mean. And has two purposes. Why do we do that? It describes the distribution. Like you can see right here, what I just mentioned. In the middle, like percentile, from again 0 to 100%, and then a standard deviation, like for the Z-score, Z has a mean of 0, a standard deviation of 1. So to the right is positive, to the left is negative. Okay. And this is one of the use of this. I'm just checking, make sure everything is working here, because this is my second time recording this. The first time I realized it's not recording, it's freeze. But it seems to be okay. All right. So here you see a research on poor attendance and taking exam. As you can see, these people had a poor attendance, and there's 665 students, with 31% of the student draw average after 5 quizzes. And here are their numbers, percentage and the number itself. As you can see, if you look at it, you can see this is bar graph. And also, if you connect those, the top, you see the normal distribution. And if you want to know how they did, if you look at those numbers at the bottom from 0 to 100 are the scores on the test. So you can see not too many 100 or even 90s or even 85, or even 80s. So most people really, if you look in the middle, are 55. 55, that's F6. So, poor attendance, that's the graph. It shows that the people have they don't have a high score. But at the bottom, you can see that there are more, let's say, there's a lot of 50s, there's a lot of 45, 50, 40s, 30s, and all that. On the different side, you see that, again, this is people with good attendance, the student with good attendance. By just looking at it, you can see that, yes, we have more 90s, 95s, even 100. And then again, here, the middle is like 70, so that's good. That means, they did much better than the one who did not attend, had a poor attendance. So once again, this is normal distribution, and the total area, that's what the statistics is all about. This is normal distribution. And any population, like I said, whether it's Albizu University, whether it's hospitals, prison, a city, you name it, any organization, they have their own distribution, like you see. And if it's normal like this, like that deep purple color, that's average. So majority of people in terms of IQ, almost 50%, right there, they in the average, they in the middle. Right there, the line in the middle says mean, that's the average. But one standard above and below mean is also called high average or low average. So it's still average in terms of IQ. And then again, you go up 2 standard deviation, 3 standard deviation and beyond, or go down. And that's where we go. Frequency distribution. We're not going to spend too much time on this. We said that in statistics, when we have a large numbers, we need to put them in a format that is more manageable. So the symbol for it was F. And the number of what is it? Is the number of frequencies, or when a score repeats itself in a group of scores. So let's say hypothetically we said that, again, we use this when we have millions of numbers, hundreds of thousands of numbers, but how can we put them in a manageable format? Here, my example was there's only 14 numbers. So, and the way, if you wanted to calculate the mean here, again, you're not going to add them up and divide it by the total number of score, which is 14. This is how you do it. Sum of the frequency, you need to have the frequency of each score, add them up then, which is the same. I'll show you in a second. Because you can see there are 14 numbers, and then sum, that's sigma, F, the Greek symbol, sigma F, which is frequency, is equal to N, sample size, which is 14. Either way is the total number of the scores. I mean, how many numbers we have? 14 numbers. And then we said that P, proportion, and then is F divided by N. F is the number of frequencies of each. If you want to know, let's say, what is the proportion of 2 in this distribution, first you need to know what is frequency of 2. Is 4, because there are 4 2's in that distribution. So 4 divided by N, N is 14. Or sum of F. Sum of F is 14. And that gives you, I believe, 0.7. That's your proportion. If you wanted to convert the proportion to percentage, you simply multiply that number by 100. Again, we covered all this last semester. So here, let's do a couple of them so you would know. Again, this is that manageable distribution. X in a statistic means scores. So you write down your scores in the first column. And they are, again, here they are, 1, 2, 3, 4. If you look at them, look, your numbers are, if you look at them, you have 1, you have 2, you have 3, you have 4, you have 5, and you have 6. That's it. That's all the numbers you have. But now, again, you need to write the frequency for each score. Like, for example, that 2 that we were talking about, we said the frequency for the 2 was 4. We need to calculate the fx. Fx means f, frequency, times x. That means 4 times 2 is 8. So the proportion of 2 is 4 divided by 14, which will be 0.29. This is the proportion, the first P in red, of 2 in that distribution. If I say convert that to percentage, which is the probability, you multiply that by 100. So 0.29 times 100 is 29%. And then the last one, which is cumulative. Cumulative means adds up, adds on. You add that 29% to the previous score, which was 14%. That comes out with 43%. So again, because 1, if you look at 1, let's say right here, 1, we have 1, 2. It has 2 frequency of 2. 1 has a frequency of 2. Fx will be 1 times 2, and P, the proportion, will be 2 divided by N, or sum of F, same thing, which is 14. 2 divided by 14 is 0.14. That's proportion. In terms of probability or percentage, you multiply that by 100, and that gives you 14%. In terms of cumulative, because this is the first number, there is no number before that. There's nothing to add to it. So it stayed the same, 14%. But the rest of them, like 3, there are 3 3s. So fx will be, when I might say, why do we use fx? In order, if you have a distribution like this and you wanted to calculate the mean, you need it right here. It says mean in red at the bottom is sum of fx divided by sum of f. Mean for frequency distribution only. We know that mean is average, and when you have a bunch of numbers like those numbers, all you have to do, add them up, divided by total, which is 14, sum of f or n. But if you get millions of numbers, like instead of 14 numbers, you got 14 millions, you don't have time to count all those numbers one by one. All you need is sum of f. Sum of fx, that's why you need the fx. Add up the sum of fx divided by sum of f. Sum of f is n, is total number 14, and sum of fx are these numbers. Fx, you add them up, 2 and 8 and 9, and then there's the rest of them. And 8 and 9 and 10 and 6. So add them up, divide them by 14, that gives you the mean. And instead of just add up all of them and divide them by total number. It'll be the same number if you do. So we also talked about these two different measurements. You need to know them. They're very important. One of them is, again, we just talked about them. It's proportion. The other one is probability. So proportion is the measurement is from 0 to 1. As you can see right there on top right square, on the right side of your screen. Probability is, again, the measurement is from 0 to 100, is percentage. We measure the probability with percentage. So what's the chances that you pass this course with your favorite grade? And you might say, whatever, 9%, 900. You say it in percentage. The probability is 100% or 90%, or I don't know. Some of you may feel less. So, but again, probability always goes with percentage or vice versa. Proportion from 0 to 1. So the reason you need to know this, and it's important, because there are numbers, the critical values in back of your book, and we're going to use them for our test of statistics when we're dealing with t-test, z-score, and beyond, ANOVA, and all that correlation. So those numbers are given in proportion, or sometimes you have to convert them to percentage, or vice versa, or you need to convert. How do you do it? If the number is given in percentage, divided by 100, and gives you the value for proportion. And if it's number, let's say 0.5 in proportion, you wanted to convert that to percentage or probability multiplied by 100, that would be 50%. If it's 0.25, that's 25%. So that measurement is very important. I hope you're paying attention and you're remembering this, because we need that. And then again, on top right of the screen, you see that mean, how to calculate the mean for this kind of distribution. The frequency distribution is sum of fx. You need to have the sum of fx and sum of f. Sum of f is n, total number of score. So if I give you, it says sum of fx is this number, 10, and sum of f is 5. What is the mean? Well, 10 divided by 5. That's the formula. Statistics made out of formulas. This formula, you need to know them. The statistic has its own language, and those are the symbols that you must learn. I'm sure some of you forgot. It's normal. It's normal if you forget the symbols and material. That's why we're doing this review. So you will get back on the track and remembering all these symbols. Again, mu, x, s squared, sigma, m, standard error, and beyond. And we'll go over them. But that's something that I can't teach you. You have to memorize them. They're symbols. It's just like if you want to learn a language, you got to learn the alphabet. So we already talked about that in basic stats. So you need to get your alphabet straight in this statistics alphabet, which is all the symbols. So when we point at the symbol, F means frequencies, P means proportion. Okay, whether probability or proportion. If it's a proportion, then that's the formula for it. This is what we talked about. And beyond. You can always look at these PowerPoints. They all available in Canvas. And so this is pretty much what we just talked about. And with the numbers, if some of you wonder, well, give me a number. Okay, so if X is 2, frequency for 2 is 4. That's what we did. N is 14. Then what would be the proportion? That 4 divided by 14.29. So 29%. And then, okay, so the probability would be, okay, so that's for that. Variability, again, we continue with variability. It's how well, and the second reason why we're using variability, because it tells us how well an individual score or group of scores represent the entire distribution. Example, in inferential research or statistics, that's advanced statistics, we collect information from sample. Then we generalize the results obtained from the sample to the entire population. And again, the little formulas that we talked about, we said there is a population, as you can see. These are the number we use. Always assume that these numbers has meaning. Let's say you got 4 students and you gave them an essay test, and the maximum they can earn in that test is 5. So you can see the first person got 1 out of 5, the second one 2 out of 5, the third was 4 out of 5, and the fourth 5 out of 5. So what do you want? You want to know the standard deviation and the variance, either for the sample or population. It doesn't matter if it says a sample, then you use the formula for the sample, the one in red. It says sample. If it's population, the yellow, then you use that formula. We did all this. In ANOVA, in a few weeks, we're going to quickly get to ANOVA. Instead of variance, sigma square, we use MS. It's the same thing. Variance is variance. So, which is a square root, a square of standard deviation. But for descriptive, we use that symbol, whether sigma square or at the bottom for sample S square. But in ANOVA, we used which is analysis of variance. So the variance has a new symbol, and that is MS, mean square. And what is mean squared? And we're going to show you in a second. So if these are your data, and then what you need to know is this formula, SS, sum of squared, deviation from mean, but for short, sum of squared. If you remember this entire definition for the SS, and I color code them for you, and you can see that definition. You can see that's sum, right? That's like green color. Squared means you multiply it by itself. Deviation means distance from mean. So that means if the mean is 3 and your score is 1 minus 3, so it's -2. That's the deviation. Distance from mean is 2 standard deviation below the mean. And the mean, which is the mu, right there, they match. Either use the definition or computation. The computation, you use sum of x squared minus squared sum of x. And make sure you know how to read these little formula. Again, the first one, it says sum of x squared minus square the sum of x. There's two different things. And we're going to go over example. And here they are. So right here, what you're looking at in those numbers, we got 4 numbers. Keep in mind, these numbers or scores, they come from people. So this means we got 4 people. You got 4 scores. A score come from people. So there are 4, but our sample consists of 4 participants. Or even if you say it's population, okay, its population consists of 4, which is unusual, but because for these practices, you're either going to use sample or population for this practice. So again, on top right side of the screen, you'll see if it says calculate the variance for this population, you need to calculate the SS and then divided by N. N is total number of scores. How many scores we have? 4. And then square root of, that's another reciprocal formulas. They, in order to complement, they complement each other. In order to convert variance to standard deviation, you need to use the square root. So if your variance is 4, your standard deviation will be square root of that number, 4, which is 2. And if I give you the standard deviation, I say standard deviation is 3 for this sample or population, what is the variance? So you square it. That's the trade-off, whether it's population or sample. For the sample, it's SS. Well, one way or another, you need to have the SS. Whether I give you the SS for this first quiz, or you have to calculate the SS using definition or computation, both the same. Is SS divided by n minus 1. So whatever the numbers are, there's 4 numbers, minus 1, which will be 3. And we call that DF. DF means degrees of freedom. That's degrees of dispersion, the spreading of the scores under that bell-shaped distribution. Where are they shifting? To the right, to the left, or in the middle? That's DF. So with DF minus 1, that's give us the sample size. Or DF, or yeah, N is DF minus DF plus 1. DF is N minus 1. Right there is written. DF is N minus 1. So if I say your DF is 10, what is the sample size here? N will be add 1 to DF, which is 11. That's the trade-off for that. There's a lot of little things we cover in here. I hope you're paying attention again, and because your quizzes and beyond, it is the same thing. And if you don't, you easily miss it. Like I said, some of them don't even need some of those questions for your quiz or even midterm exam. They don't even need a formula. I just say, well, your standard deviation for this sample is 4. What would be the variance? And that's it. Variance is a square of S, a standard deviation. Just a square of 4 is 16. I said that at least 2 times. So these are little things you may want to take a note, or before you take your quiz, and make sure you master all these information, basic little stuff. So again, 2 ways to calculate the SS. You can see definition and computation. So let's do it. Let's do this. Okay, this is our data. As you can see, all we have is the X, the score from 4 people. And question says whether they wanted to for you to calculate the variance or standard deviation for population, or variance or standard deviation for the sample. And here they are, all calculated. Again, keep in mind that X, red X, those are the scores. Any of those formula, on the right side of the screen, again, they all have SS on numerator, the top. So what does that mean? It means you got to calculate the SS first, whether you're using the definition or computation. The computation is really easy, and we go over that in a second. But let's use the definition. We said definition for SS is sum of squared deviation from mean. If you write it down like I did at the bottom of that slide, and then you number them, those 4 words, meaning you have to calculate the mean for those. Again, right now the data we have is that X, red X and red numbers. So that's your data. So focus on that. You need to calculate the mean for those numbers, 1, 2, 4, 5. And then number 2, deviation. Calculate the deviation distance from mean. Then you do the square, and then sum them up. All right, let's do it. Mean for those numbers, you add them up. 4, 5, 9, 10, 12 divided by 4 is, so sum of X, sum of the score is 12 divided by N, which is the total number of score, therefore, is 3. So mean, mu, is 3. We did mean, okay, mean is 3. Next is deviation, mean distance of each score from the mean. So the first score is 1, and the mean is 3. So 1 minus 3, that's the second column to the right, when it says X minus mu, mean of X. So that's deviation. That would be -2. The second would be, again, 2 minus 3, -1, 4 minus 3, 5 minus 3. And those are your number. I circled them in that fashion. Those are your deviation. We said in ANOVA, I hope you remember this when we go over ANOVA, this is deviation. Variance in ANOVA is MS, means mean squared. So mean of these numbers will be your variance in ANOVA. But again, for now, let's put that aside and focus on this basic. This third step is the square. Now you need to square your deviation. Those numbers that we square, you need that, those numbers that we calculated, deviations, we need to square them. -2 will be 4. -1, 1, 1, 1, 2, 4. So that's, you can see in terms of formula, X minus mu, mean of X, square, a 2 on top. We did. The last thing is sum them up. 4 plus 4 plus 1 plus 1 is 10. So our SS is 10. That's right there. That's right there, the bottom one. That's how we calculate it. If you want to use the top one, the bottom one is the computation. Then computation is sum of right there, right under the thing, the table. It says sum of, you need to have the sum of X squared. The formula, it says SS equal to computation, right there. SS equals to sum of X squared minus square the sum of X divided by N. So we need to know what is sum of X squared. X Again, that's our data. X, the red column. We need to have an x squared column. So that means you square those numbers. 1 will be 1. The square of 1 is 1. The square of 2 is 4. You move to the left. It says the first column, x squared. The square of 4 is 16. The square of 5 is 25. Add them up. Sum of x squared is 46. So the formula is sum of x squared, which is 46, minus the square, the sum of x. Sum of x is right there. X is 1, 2, 4, 5. You add them up is 12. Sum of x means sum of x squared, the sum of x. So the square of 12 is 144 divided by n, which is 4. 36. And then 46 minus 36 is 10. Either way, your SS is 10. And we did that. So once you got the SS, you're home free. Any of these formula on the right, it should be piece of cake for you. If I say on top right side of the screen, if I say calculate the variance for this population, you already calculate the SS. It doesn't matter whether it was a standard deviation or population. So SS is 10. 10 divided by 4, which is n, 4. N is number of participants or scores. So 10 divided by 4 is 2.5. That's your variance. If I say, what's the standard deviation? You should know that square root of variance is the standard deviation. So the square root of 2.5 is 1.58. That's your standard deviation. On the same token, in black, sample, if I say variance, calculate the variance for this sample, then again, SS is 10, you already calculated one way or other. Divided by DF. DF is n minus 1, n is 4, minus 1 is 3. So 10 divided by 3 is 3.33. That's the variance for the sample. And if I say, what's the standard deviation? Square root of that number, square root of 3.33, it's 1.81 at the bottom. And then again, keep in mind that if you wanted to calculate, if it's in some of the questions, it says calculate the DF, but you're given the SS and SS square, then SS divided by SS square gives you value for DF. Keep in mind your quizzes, your exams are all open book, okay? And you have access to everything. We'll make sure you understand the symbols, the meaning of them, and read the question. Make sure you know what the question, what the problem is asking you. Pull out the right formula, plug in the numbers. Again, DF is n minus 1, and n will be DF plus 1. Make sure you note that. Again, if your DF is 3, then what would be n? 4. This is how we do these, all of them. Again, for ANOVA, just a refresher, remember that the same formula, SS over N, but the symbol itself is not sigma square. It's MS, mean of a square deviation, or mean square. X minus mu is deviation, distance from mean. X is your score, mu is your mean. Subtract those two, and then square it. That gives you deviation. Okay, so That's your deviation. The square deviation. Mean is not mean of deviation, but mean of square deviation. So whatever your deviation is, right here, you can see that in the middle, whatever your deviation is, you square it on the right side. And the mean for that will be your variance. It's the same. It'll be the same number we got. That's what we use for ANOVA. It's the same thing, really. So with that in mind, we move to z-score quickly. And once again, you have access to these materials. Please read them before we move to the next and next level. Because if you don't, if there's reason that we're reviewing the materials. If you don't understand the symbol, then you don't. They're pretty much, they're all the same. Once we get this out of the way, we go over one test of statistics and another. From z-score, we go to t-test, to different types of, again, t-test, different types of ANOVA, and then correlation, non-parametric test, and beyond. But the procedure, hypothesis testing, that's what we do. We test your hypothesis, your research hypothesis, using these statistical procedure. The procedure is same for every one of them. There's 4 steps that we're going to go over today, but it'll be the same for every one of them, but different test statistics. So we said that also you need to know these materials from your comprehensive exam. I don't know if you still have it or not, but we used to have it. There are 2 different types of z-scores. One that we're going to, right there you see, is for single score. Simply tells us where do we stand in a crowd. If I say your IQ is 130, what does that mean? Z-score tells us. Z-score is a standardized score. IQ is a standardized score. We use z-scores when we work with standardized tests, such as IQ, such as ACT, all those college examination, college entrance examination, some of the psychological tests, Wisconsin card sorting is a standardized test. What does that mean? That means they have a fixed mean and a standard deviation. It never changes. Like for the Z, mean is always 0. The standard deviation for the Z is always 1. It doesn't matter which Z-score we use. For the IQ, mean is always 100. That's average mean. The standard deviation for IQ, always 15. Standard, that means whether you take your IQ here or in New York or in Canada, if you use the standardized IQ test, not the Mickey Mouse IQ test on the internet, wherever you take it, it tells you that where you stand. Average, above average, how many standard deviation. If you take your GRE, ACT, SAT, all these tests, like let's say GRE, some university require that you have to have a certain score. It doesn't matter. That's a standardized test. In which states you are, still, is a standardized. So mean will be, let's say, if ACT, let's say 500. So they say, well, we want you to have at least 500 for SAT or SAT. So what is the job of this z-score? It tells us that how many standard deviation we are above or below mean or average on whatever we're doing. Like in a classroom, a student asks you, where am I standing in the class? And you say, oh, you 1.5 standard deviation above average student, or 2 standard deviation, or 1 point standard deviation below. You need to pull up a little, become average and all that. So we said that this is the formula, and z equal to x mentions your score. Let's say, again, keep in mind, you use standardized test. You got to use standardized test. I know one of the questions pop in your mind right now, well, what if we're not using standardized test? What if you use some depression test? We don't have a standardized depression test or stress test. Then you can't use z-score. You got to use t-test. That's why we have a t-test, which is just like the z-score for research. This is not for the research. This is for single score, just one. It is for research, but not for group of people, not using sample, just single, one person. Your score is 130, and you don't know what does that mean. So I will put it right there. I want to see Z will tells me where you stand. Your score is 130, which is X, minus the mean of IQ, which is 100. 130 minus 100 is 30, divided by standard deviation of IQ, which is 15. 30 divided by 15 is 2. So that tells you that your 2 standard deviation above average Joe. That's the job for it. But for the problem solving in the class, there's different varieties. I gave you how to, like sometimes I give you the z-score, for example, on top left, left screen. I ask you, what's the score here? The standard deviation is 15, z is 4, and mean for IQ is 100. What's the score? And that's how you calculate it. Well, what's the mean? What's the population mean here? What is the standard deviation and all that? If you look at those samples that we covered, hopefully you have them, then you get an idea. Well, for this one right there, see if you can do this. If the mean is 80 and standard, this is another standardized test. We don't know the name of it. We have a standardized test. Keep in mind, in z-score, you always use a standardized test. In reality, if the test is not standardized, then you don't use z-score. But again, I say we have a standardized test with mean of 80. Mu is 80. A standard deviation of 10. What would be the z? So you put them in there. It's that easy in that formula. I know. If you have a problem, let me know. Okay? So you can see the symbol mu goes right there, and that x x is 70. So your score is 70. If x, your score is 70, minus mu, which is 80, divided by standard deviation, which is 10. What would be your z? This is the z-score for sample and research. So from this point on, we really now start leaning toward inferential statistic. What does that mean? It means we draw conclusion from our sample. As you can see, z-score for sample. And sample, you don't have one person or two. You got to have a bunch of people. Like we talked about in the beginning of this lecture, we wanted to know what is the z-score for, let's say, albizio university students or graduate students. Okay, so we need to have a sample, like we mentioned in the beginning, because statistics, we're talking from this point on, is all about research. And that's why it's important that you need to have this class to help you with your doctoral dissertation. So you take a sample, 200 graduate students, and give them the IQ test. Calculate their mean. Somebody has IQ 130, somebody 110, 115, and beyond. I'm sure everybody's above average, because you can't be in graduate school with a average or below average IQ, I'm sure. So you calculate the mean for all these people IQ, and that would be M. That's mean average for the score, minus the mean for the IQ, which is 100. So let's say the mean this time, the average for all those people is 110 or so. And let me see if I have an example here. Right here, the mean is 110, and the mean for IQ is 100, and we got 100 students. Of course, we know the standard deviation is 15. First thing you do, is you calculate. First thing you do, you need to calculate the standard error of the mean, the one what we talked about. So how do we calculate that? The standard error is a standard deviation divided by square root of sample size. And then again, these are variation. Like if I give you the standard error and the sample size, that's the square root of that. I ask you, what is the standard deviation? Keep in mind that, the first one, the sigma, is a standard deviation. The second one, sigma m, is a standard error or standard error of the mean. But we say standard error, that's it. And then again, if I ask you, what is the sample size here? That's one way to calculate your sample size. Your standard deviation divided by standard error, whatever you get, square it. And then again, for the formula itself, we said that M sample mean minus population mean divided by standard error. That's the general formula, and those are the deviation. Those are the derivatives. Sorry, not deviation. Derivatives mean we can generate formula from a formula by using there's a little algebra or cross multiplication and all that. You don't have to know that to come out how I came out with these formulas. But you can solve, for example, that the main formula is right there in that square. But if you ask you to solve this for the standard error, it's already done. A standard error is m minus mu divided by z. I give you those information, the z-score, the sample mean population. And if I say, what's the mean for this sample? That's how you do it. That's z multiply, which is point, a standard error plus mu. And if I ask you, what is the population mean? Sample mean minus standard error times or multiply 0 as z. This is how you calculate the standard error. We said the standard deviation divided by standard error, but it has its own derivatives. That means if I give you the standard error and n, you should be able to calculate the standard deviation from a standard error. And then again, sample size from standard deviation, standard error. We already mentioned that. So here's the example. If we have all these examples, we have, let's say, 100 students from Albizu University. That's 100. With the mean of 110 on IQ. We test their IQ. All of them, the average IQ will be 110. Then mean for IQ is 100, standard deviation for IQ is 15. First thing first, I like to calculate the standard error denominator at the bottom, which is standard deviation divided by square root of n. Then you go to at the bottom of your screen, bottom right. Then you move to the left, which is the standard deviation is 15 divided by a square root of n. N is 100. A square root of 100 is 10. So that would be 1.5. So the denominator will be 1.5. And numerator on top will be 110 minus 100, which is 100, which is 10. So that would be 10 divided by 1.5, which is 6.66. That would be Z. That means the students are 6.66 standard deviation above average, which is good. So then again, every test statistic that we're going to cover uses there is another topic, it's called power, which we'll discuss later. It's about power of your research, how to increase the power of your research. But one thing we're going to cover here, and in every test statistic, is called effect size. And they all have different names. In this case, for the z-score, it's called Cohen's d. Cohen's d is the effect size, which is the difference between the means in a treatment condition. How large the differences are, we wanted to know. Meaning the result from a research study is not just by chance alone. It means there is a real big difference. In your research, you need to calculate, APA wants you to calculate the effect size. So the difference, whether you compare in two groups or you compare in your group with the mean of IQ, the effect size is the difference between the two mean. Now, we know mean for the IQ is 100, but if your mean for your sample is almost 100, if you look at my hand, 100, these are two different distributions. 100 and 100, you see them at one mean, 100. But if it's difference, one of them 100, one of them 110, you see that there's two different distribution, and the bigger the difference, they separate from each other, and that's what you want in research, because null will say no difference, nada, zap, zero difference, but you wanted to really, you believe that there is a difference, real difference. And that's how it is in all of them. So anyway, here I showed my hand that that's how it is. If you use in the experimental research, which you have two groups, control group and treatment. Treatment is the one that get the real treatment or real pill, real medicine. Control gets the so-called placebo. Let's say and if you're doing therapy, will be control group where it gets pep talk. But the treatment get real therapy. Let's say cognitive behavioral therapy, CBT. So you wanted to see after 3 months which group did better. You give them depression test, and if both have the same mean, then you only see one distribution. D, effect size, 0, no effect, it's not working. But the bigger the differences are, like you can see here, the more effective your treatment is. All right, that's the research part. We'll talk more about this. And then again, D, effect size, have its own formula. And you can see the symbol is D, lowercase d, m minus mu, just like the z itself, but instead of divided by a standard error of mean, it's just divided by the standard deviation. And of course, those are the different, like if I give you the other information and if I ask you to what would be standard deviation, these are the derivatives, or what is the mean, or what is the mu derivatives. Yeah, it's good to have these handies. It's good to know all these symbols. So what's the mean? Well, if you want this mean, make sure you have the D, you have the effect size, and you have a standard deviation. Multiply those two, plus add it to the mean, which is 100. All right. So again, that's another example. Oh, this is what we did, really. This is an example I showed you on that slide, but it's also repeated here too. And with all those calculation. So again, we only did that part. We calculate the Z. Now, if you wanted to calculate, for example, sigma, that's how you do it, 1.5. M, that's how you do it, and mu. So look over them. We went over this last semester, and then that also effect size. That's how you calculate it from all that data that we have. The data are on like in the middle of the screen on the right side. Mean is 110, mu is 100, standard deviation 15. It's the same data that I showed you. So hypothesis testing, and that's what really the descriptive statistics starts. It's all about hypothesis testing. Once again, what is hypothesis? It's your research topic. You're saying something, okay? Now you have to test that hypothesis to see if you're right or not, or see if the findings of your research support your hypothesis or refute. In both cases, you learn something. It's not like you wasted your time if you refute, but it's always good to support your hypothesis. But either case, you did your research and you found out something. And let's say if you say something like consumption of sugar will increase the hyperactivities in children. And then you have a sample of children, you put them on a high sugar diet, but then you realize that it's not really the sugar. Oh, then you realize that the sugar has nothing to do with hyperactivity, which it does, but that's just the example. So whenever you conduct research, again, that H1 is you. That's the researcher or alternative hypothesis. H0 or H naught means zero, nada, zaps, zilch. It says nothing. it basically tries to discourage you, say, no, I don't think so. If you're doing a correlational research, null is 0, means your correlation is 0, means no correlation. Don't waste your time. If you, again, you're saying there's a difference between your group and the control group and your treatment group, null says, no, it's the same thing. Your medicine is not working. Your therapy is not working. At the end, the mean will be the same. I don't think so. So you got to test your hypothesis and disprove the null. And it doesn't matter which kind of test the statistic you use. You got to somehow statistically prove that whatever treatment you're using, it make a difference. There is a difference. Like I said, if you can, it's not end of the world. And it's not like you wasted your time. It means you just don't. It doesn't. You couldn't. You failed to reject the null. That's how they say it. Of course, you're not going to write it down. You gotta, in your research, you just do your calculation, and that's what we're going to do. We use SPSS with our data, and then we got to be able to read those tables. What does it say? It says no difference. So we either accept the null or reject the null. Or we either reject the null or fail to reject the null. It's same thing. Same thing. Or retain the null. That means accept the null. So different people say different words, but again, it's either or. You accept or reject. So null hypothesis, H1 alternative hypothesis, HA, we refer to it as H1 or HA. Different textbook, different symbol. Also known as the researcher hypothesis. So here's some example of research. Again, it says that hypothesis is really educated guess or statement. So selecting a problem to investigate is your research topic or hypothesis. For example, the effects of TV violence on children, or it's a different ways. The way you state your hypothesis calls for different types of research. Like if you say the relationship between TV violence and aggression in children, well, right there. The relationship, this is a correlational research. It's nothing about effect, cause and effect. So your research question is, does TV violence, again, it can't be, for example, it can be that TV violence cause, this is another one, aggression in children. The research, okay. If you say correlation, there's correlation. If you say cause, if you do, does TV violence related to aggression? Okay, that's also correlational. Or if you say the violence may cause, here you're saying cause, aggression in children, or TV violence may be related to aggression in children. Again, these are different types of research. We'll talk about them. And in general, this is another topic. It says that all these variables may complicate during the pregnancy and may cause, this is cause and effect research in autistic children. In general, what you see at the bottom is First of all, here's my suggestion for you if you haven't selected your topic yet. You don't get into uncharted territory. You don't get into the area that is not your expertise. When you select the topic, even though I hear some people saying, oh, that's wrong. How can you talk about something that you don't know anything about? Like you talk about UFO, but your major is human services or psychology. What do you know about UFO? You got to go there and spend years of investigating that. The best is to stick with your expertise. Again, whether you're working, let's say you're a counselor, you're working with children, with autistic children, you've been working for many years and you want to find out something and you learn many things. You find that what is it that causes or what is it that relates to autism? And based on that, you come out with a hypothesis, a topic. So as you can see here, you just like this hypothesis, something that has to have a root. First, you gotta have information. You gotta have some kind of expertise on, let's say, autism, or or ADD, ADHD, or any kind of human services topic. Then you gotta have a knowledge, read a few books and understand what is this about. Then come out with your own theory. Again, theory could be right or wrong. And people say, I have my own theory. Okay. You can't tell them, oh, no, that's wrong. It's theory. We know theory could be right or wrong. But in order to test your theory, that you need to come out with research question. That means clearly, concisely. You got to say what you have to say that anybody can understand. Don't come out with a vague question like you don't even know what you're talking about. So that's not good. It should be concise. The topic, clear and concise topic. That is your hypothesis. Okay? And then you test that hypothesis, whether you're right or not, based on the data that you have. So in order to do that, there are different ways to do this. You either use the non-directional hypothesis. Non-directional, that means you don't, let's say, consumption of, let's say, sugar increases the hyperactivity. Now that is directional because you're saying increase. My hand's going the wrong way because I go right here. I see on the screen go left, but increase means to the right. If you say consumption of sugar decrease, then to the left. That is directional. You're saying that, that's directional hypothesis. But if you don't say it, like this one, it says, watching Sesame Street may affect future performance of children in high school, or consumption of sugar, may affect the hyperactivity. But you're not saying increase or decrease. This is good. It's always best to have non-directional hypothesis, but it really, in reality, doesn't matter. I can't tell you that use directional or non-directional. It's your topic, but you know whether it's directional or non-directional. When you're not pointing to the increase or decrease, or low or high, then it's non-directional. But if you do, then it's directional. So if you have any question, please let me know. Just email me and I will respond. But if it's non-directional, again, like I mentioned, you're either on the right side, the highlighted dark blue, you're saying increases, or if you say decreases, it's your hypothesis. If you say consumption of sugar increases the hyperactivity, that's the one on the right. If you say decreases, on the left. If you say have an effect somehow, you're not saying that increase or decrease. So that would be your topic. So null always says the mean is either equal to 100 for the z-score or less. That's null, H0. H1 or HA, we go by H1. It's the same thing, alternative hypothesis or researcher hypothesis. H1 is us when we conduct research. We say no, the mean will be greater than 100. Like let's say you do a research at Albizio and you think the mean will be greater than 100 because you think, what is your graduate student? So it's got to be, the IQ is going to be greater than 100. That is directional. Okay, because the population mean is known, again, if we know the mean for our population, whatever we test in them, like if it's IQ, we know the mean for IQ is 100. So what kind of test statistic we're going to use for this research? Z-score. If you use depression test, we don't have a standardized depression test or stress test. Every one of them has different mean and standard deviation. So for that, you cannot use Z-score. You got to use t-test. That would be our topic for the next lecture. And in doing that, we test our hypothesis. And we're going to go over this again next week and it's same for every test, the statistic that we're going to cover is going to be the same. For example, the first 4 steps we're going to use for hypothesis testing is step 1, you state your hypothesis. Whatever you say. In this case, we're saying that population mean, we're saying that that our mean is going to be greater than 100. Null says no. Null says the opposite. It says either it's going to be equal or less. I don't think so. That's what it's not going. It's going to be same 100 or less than 100. But again, it depends. If you use a directional and then will be different. If you use a critical, you say higher, then like or lower, then null will say whatever you say. Null says the opposite. If you say greater than 100, null say no, less, equal or less. If you say less, null says no, more, higher, same, equal or higher, the opposite of what you're saying. If you're saying is equal to 100, null says no, it'll be same. No, if you say it'll be, you can't say equal. You say either more or less, or you don't know, two-tail. But if you don't say anything, null says it's going to be 0. 0 means the same. That means if you say the mean is going to be 110, null says 110. But if you say it's going to be greater than 110, null says no, it's going to be same or less. If you say it's going to be less than 110, null says no, it's going to be greater than 110 or equal. Okay, again, this is what we're going to talk every time for each statistics, one tail or two tail. So in this case, you state your hypothesis. You say it's going to be mean is going to be greater than 100. Null says no, it's going to be less than 100. And then if it's one tail, then at the alpha, this highlighted blue is called alpha or rejection zone. If it's one tail, then it's 0.05 means 5%. That's what we talked about earlier. That's proportion, 0.05. So in percentage, probability will be 5%. That means there's 5% chance that even if we reject a null, because it's research, we don't use everyone in population. Even if we reject a null, it's not written in stone 100% that it is so. Keep that in mind. Every article you read about research is not 100% true. It's based on those participants in that research, is the result of those participants' scores in the research. So with alpha of 0.05 means there's still 5% chance, even though we reject the null and we make a difference, but still 5% chance that our finding was based on error involved. But again, we're 95% correct if you look at it that way. CI is opposite of alpha. We'll talk about that in a second. So based on that, again, we do our calculation, and then if our calculated z-score, in this case, fall into that rejection zone or rejection region, then we reject. If it falls short, then we fail to reject. And again, we're going to do, if you work with T and then go over the example. So this is, again, step 3 is calculate the z-score or t-test or ANOVA or correlation. It's all the same. In this case, we did calculate the z, and right there, those are our numbers, and we came out with 6.6. So we wanted to know whether we reject or retain the null right there. Okay. Once again, if that number falls 6.66, again, the critical region is 1.6. So 6.6 will be deep in that red zone or rejection region. That means we reject. But if instead of 6.66, if we come out with, let's say, 1.2, and we'll be here, then we are in a fail to reject region. We fail to reject the null. So any number greater than 1.645 is rejection. We reject the null. And again, where do we find that manually? For the z-score on page 702. And for that, you need to calculate the DF, degrees of freedom, and n minus 1. If you got 4 people in your sample, even though you don't really do research with 4, but to ease up the calculation, we use a small sample for the calculation. So your DF will be 3. If you have 100 people, then your DF is 99, n minus 1. And then what you need, 1 tail or 2 tail. Then you use, for example, 2 tail, then you look for the alpha of 0.05. And based on your degrees of freedom, it tells you the critical value. Critical value for that number. If that, again, if your calculated T, the 2Z, these are z-scores, okay? And the calculated z that we calculated was 6.66. If that number is greater than these numbers, then it's going to go in the region, the rejection zone. If it falls short, fail to reject. So let's just, okay, let me check something here. Okay. So again, in social sciences, we only use alpha of either 0.01 or 0.05. And of course, one tail or two tails when it comes, to the z-score. But in mathematics, they use the other kind of alpha level. Once again, a CI, confidence interval, is opposite of alpha. That means your alpha, like we use the alpha of 0.05 here, which is 5%. That's 5% chance we could be, what we found was by error, 5%, even if we reject the node. So what does that mean? That means 95% is CI, which is confidence interval. In other words, you can say with 95% confidence that yes, we reject the node because our data shows. That means there's something there. That means like sugar, for example, it does increase the hyperactivity and so on. So, okay, so again, that's why you need to have a book, textbook. And if you use the same textbook I used, and I mention it is in syllabus, then you can use that page number and all that, because we have to have critical values for all of them. This is another example, research example. What kind of hypothesis is this? Okay, see if you can answer that. Short-sighted people are more intelligent. Remember, there are non-directional or two-way hypotheses. And there are directional, where they tells you more or less, high or low, increase, decrease, which is one-way directional, either right or left. Remember that. And then in terms of SPSS, this data, again, is from the test construction book that we used to teach. I also, so you know, implemented test construction in the stats, especially this one. Reliability. Last semester we did reliability, validity, and beyond, standard deviation, variance. Again, when you create a test, it tells us, like, for example, here you have 10 people, and then you give them a test consists of 5 items. These are non-dichotomous. Dichotomous mean true, false. They either get 0 or 1. Non-dichotomous can be essay, like, or multiple choice, Now, multiple choice is also dichotomous because you either get it or you don't. But for example, essay 1 to 5, right? So you can see person 1, question 1 got 5 out of 5. Question 2, 5 out of 5. Question 3, 4 out of 5. And then person 2, question 1 got 2 and 2. That's how you read it. And then you see the total for each person. And then item mean for each question was calculated, item variance. So if you look at those variances, you see the lowest is 0.4, which is question 3. If you have to get rid of one of these questions, it will be question 3 or item 3. Why? Because it has the lowest variance. Variance is about quality of items, for example, in test construction. So you can do this. Open your SPSS. You should know because we already done it. You all did it. And I'm proud of you. For those of you who had that basic stats and did all of your SPSS, it's very important because in reality, you don't do any manual work in real world. It's all using technology. Even your research, you're not going to do any manual calculation. You got to use SPSS. So anyway, and the way we did it was once you open your SPSS, you put in, you go to variable view and put like either X1, X is a score. Also, you can put Q. Q means question. Q1, Q2, Q3, there are 5 questions, or X1. That's how you name your variable. And then click on data view and you'll see them, those 5, Q1, Q2, Q3, all the way, or X1 of them. So under X1, you put those numbers, like 5, 2, 4, 2, right here. On X1, you put 5, 2, 4, 2, and all that. On X2, you put these numbers in each column. And this is your data entry. You enter them in there. Then you go to analyze, you go to descriptive statistics and descriptive. And again, see, all that work we did within seconds, you transfer your information from the left here to the right. And then you click your option, and then you click whatever, especially the stuff we talked about tonight, mean, median, you know that. Those are calculate mean, median, standard deviation, variance, range, and all that. Click on those and click continue, click OK. And you should have come out with the answer. Anyway, also you can do graphs and charts. It gives you right there choices if you wanted to do the graphs. Okay, we're going to do more with heavy duty stuff coming. So yeah, so that's it for now. Please go over the next slide, whether it's PowerPoint 5 or 6, whatever you call it, but it's the t-test. Sometimes the number don't match. So please do your SPSS assignments and your quiz so we can get ready to move forward. Other than that, thank you for your time, and please let me know if you have any question or concern. Have a great week.